Okay, let's go ahead and get started.
Right.
As you probably may have noticed, there's no chapter from the book tonight. This section has a presentation on UML, which is comes from some other source. Okay? But we'll go ahead and use it. And it does explain what UML is. How many here have used or are familiar with it? You're familiar with it? Okay. You know what it really means, right?
Unified modeling language?
Yeah. And what it's really talking about is visualizing what we're doing rather than writing down bullet, 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 bullet. That's the whole idea. We're going to go through and see some of the aspects of it. So talk about a visual modeling first before we get into the discipline of UML. But here's a business process. You have somebody puts in an order, we have an order taker, puts it into the computer, goes to the computer, and it's going to ship via truck or train. So it's a business model. But you can follow it that way. Here's a computer system. We've got multiple users connected to some kind of a server. Okay? So it's just standard graphical interfacing. You can look at it as this. You take ideas that you are, I think these are brains. You take ideas from your business model and you transpose those into the computer domain, but the two really have to map to each other. You've got to be able to see the process logically from your brain standpoint, or the user does, without knowing anything about IT. It also manages complexity. So you can see in the background, this could be a very complex looking thing, but maybe we can make it look a lot easier using some kind of visual modeling. Again, one of the interesting things they're doing here is they're showing reusable components down here. So once you've built some of this is going to help in thinking about modularity in programming by modules. Because when you do this, you end up with modules, you say, okay, now that's kind of general. I could probably use that in a lot of different places. So what is UML? Well, it stands for Unified Modeling Language. Combines the best of the form from data modeling concepts, which is entity relationship diagrams, business modeling, object modeling, and component modeling. They put it all that into one thing called unified. That's why they call it unified modeling language.
Professor, I have a question.
Yes.
What's the difference between UML and activities graph?
An activities
Graph.
graph? Graph. Oh. An activities graph can be done with UML. What UML does is it has a discipline of what arrows look like, what dotted lines mean. So it's brought some discipline to it. But you can do an activities graph using UML. So you're in the right place. It's the same idea. In fact, we'll see one as we go through here. So it's become the standard language for visualizing, specifying, constructing, and documenting the software-intensive system. The more software-intensive you get, the better this is at showing what's going to happen through the system. And we're going to have a sample system here in a minute. And maybe this is closer to what you were talking about. So it can be used with processes, which is activities, throughout the development cycle and across different implementation technologies. It doesn't talk about, are we using a blade, or are we using some other server or network, or it doesn't talk about that. It talks about getting the job done, but it helps in the design stage of your project. it can display the boundaries of a system. It's good to know where our system stops. Because sometimes, and you've probably seen this, if you just hire a programmer to get a job done, some programmers will take off and do a whole bunch of pretty stuff. But the UML diagrams that you do first define the boundaries. This is all we're doing. Don't go out there. We're just doing this. We use cases with use cases and actors. We'll go into what those are. We're going to illustrate use case realizations with integration diagrams. We're going to do that. Represent a static structure from a system using class diagrams. And then you can model the behavior of the objects with state transition diagrams, another thing. We talk about the physical implementation architecture with component and deployment diagrams. And we can extend the functionality with stereotypes. So let's take a look at some of those. And I think some of those are in your project requirement, aren't they?
State diagram.
Yeah.
Well, actually, that's actually a homework assignment.
Yes, it was. That's right. So, we've got ESU University wants to computerize their registration system. The registrar sets up the curriculum for a semester. One course may have multiple course offerings. And what they mean by course offerings are multiple days of the week with multiple classes. So you take section 01, section 02, whether online or in class or whatever. Students select 4 primary courses and 2 alternate courses. That sounds like 18 hours to me. And I think that's what we did when I was in school. Once a student registers for a semester, the billing system is notified. Now, the billing system is notified from what? Does it get notified every time he enters a course, or does it come off his schedule? Okay. In this case, they're going to say it's after he signs up for 4 or 5 courses, then it's going to take everything off of his schedule and figure his billing. Okay. And it could have been either way, couldn't it? So wouldn't it be nice if the diagram made it very clear which way it's going to work? And that's what we're concerned about. Students can use the system to pull their schedules after the time of registration, or to change courses during the add drop. Professors use the system to get the rosters. And use of the registration system are assigned passwords, which are used at login validation. What does this look like? Does it look like requirements? In a generalized, high-level
It's missing
way.
a key word in each of the sentences.
So, we've got actors. Here's what actors are. They're the people. Or they could actually be other processes. Okay, but in this case, they're going to be people. We've got the registrar, maintains the system. We've got the professor, who pulls the roster. We've got the student, who inputs his requirements for classes he wants to take. And when they're all put together, he's got his schedule. And then we've got the billing system, which starts billing once the student gets their schedule put together. And this is key. Actors are not part of the system. Actors are sitting outside the system, drawing information out of the system or putting information into the system. So let's look at some use cases. And we're going to look at 3 of the needs from this system. One is you've got to maintain the curriculum, right? You may have, a professor might request the roster, and a student is going to maintain their schedule. But the system has to do that for them. But that's their desire. So a use case is a sequence of transactions performed by the system that yields a measurable result of values for an actor. So an actor is going to request something or originate something, and the system then takes over and does something. The transactions for maintaining curriculum can be isolated. The transactions for requesting a roster and schedule are different things. Those are each use cases. So those are definitions of use cases. So the use case describes the desired external system behavior from the point of view of the actor, the user, and thus the requirements that the system must fulfill. The use case is a description of what the system must do, not how it's going to do it. So we're not getting into designing software so much as we're designing the system so that we can then begin to design the software. So it's a pattern of behavior the system exhibits. In each case, a sequence of related transactions. This looks like the previous slide right there, but we can go get a little more detail here now. Actors are examined to determine their needs. The registrar maintains the system. The professor requests a roster. The student maintains the schedule, and the billing system receives billing information from the registration. But where? Well, we'll see that in the use case. So we need to document our use cases. Documentation would show the flow of events that's created for each use case, written from an actor's point of view. So if you're a student, the use case would tell you what you as a student would do or see. For instance, it said up front they need to enter a password, right? So you would enter a password. You might want to check to see if it's within drop add, and if it's within drop add, then you would have choices. Do you want to drop? Do you want to add? Of course. Do you just want to see your schedule? But those are the types of things we're looking for in the use case. What is it going to look like to that particular actor? What starts it and what ends it? Okay, so how about maintaining curriculum? That was that first oval down at the bottom. So this use case begins when the registrar logs into the system. So there's the start. It's started by the registrar logging into the system. The system verifies the password is valid, and then that's event 1, and prompts the registrar to select the current semester or future semester, event 2. The registrar enters the desired semester. The system prompts the professor to select the desired activity. Remember, he's maintaining the curriculum, which means he's adding and deleting courses. Or he may be just reviewing. And of course, after he's done all that, he quits. So if the activity is selected as add, then we have a subcase, S1, for adding a course or subflow. If he wants to delete, we have S2 that goes through deletions. If he wants to review, it's S3, and so forth. And if he wants to quit, the use case ends. So there's a description for documentation of what this particular use case needs to do. So here's the use case diagram. If you look at students, they input into the maintain schedule area, don't they? Because that's the student area. And notice in this case, that's where billing comes out. But like you said, it could have been somewhere else, couldn't it? It was the decision of this college or university to do it this way. The professor, he inputs a request for a course roster. the registrar inputs into maintaining the curriculum. So those are very high level use cases or use case diagrams. It's an outside view of the system because we're not talking about how the system actually works. Now, interaction diagrams describe how the use cases are realized in interactions among societies of objects. So when we begin to see these use cases come together is when we begin to see an interaction diagram. And there are sequence diagrams and there's collaboration diagrams. So let's take a look at a sequence diagram. Sequence diagram goes by time. So this is the start over here, it's the end. The student fills in information into the registration form and submits it. From the registration form, it goes into the add course, Joe, Math 01. So it's seeing if we can get Joe into Math 01. And that goes into the registration manager where we know whether that course is full or not full, or if it even exists anymore, so forth. So it asks, are you open? Meaning, are you a full section? If so, add Joe. Then that's Math 101, but we haven't chosen which section we're going to put him in yet. So then we go down to the different sections and ask if they're open, and then add Joe. And as you all know, you can pick the section you want to be in, right? Because of the time and day that it's meeting on.
There's only one option for this class members.
Yeah, because we only had one time. Yeah, right. What's kind of interesting is this is suggesting that probably to save processing time before you even go to the sections, if all the sections are full, it'll stop at the course level. So, class diagram shows existence of classes and their relationship, not course classes. Classes of things, we're going to talk about classes here. And their relationships and logical view of a system. UML modeling elements in class diagrams. Classes and their structure and behavior. We're going to look at association, aggregation, dependency, and inheritance relationships. And these now have to do with some of the symbols that we use in UML. The multiplicity and navigation indicators, we're going to use those, and the role names. So let's look at the next one, show us one. Now, what is a class? It's a collection of objects with common structure. So it can be processes in common, or it can be things that are going to be in the file, like people. It can be the courses, for instance. Classes are found by examining the objects in sequence and collaboration diagram. So we're going to see that when we get into this. The class is drawn as a rectangle with three compartments. There's the class, there's the descriptors of the class, and then there's the functions against the class. And they should be named using the vocabulary of the domain. Naming standards should be created. And this is created by you all, the designers. But you want to make sure you keep the standard. All classes are singular nouns, starting with a capital letter. So now we're getting into some things that are dependent on UML users. So here's some classes. Remember the registration form that the student uses? That's the form for their screening, right? Where they're going to fill in their request. The registration manager is a process. Student, though, is a user, aren't they? Professor. Course offering, this is the one that with location and time and so forth in it. But the courses are the mother of this. It's the course itself. And then there's a scheduling algorithm that can be called. It's a process. The behavior of a class is represented by its operations, and that's the third area in the rectangle. So notice registration manager has, one of its operations is add course. What else does it have? Delete course. And what they have to do is put student and course, because in this case we're talking about adding a course for a student. So adding a student to a course. So there are all kinds of other activities within registration manager. This is add course, which means add student to a course. There's also going to have to be one for adding new courses or deleting old courses that were taken out. Attributes are those things that give more meaning to the class itself. So a class offering has a particular number, this would be the section number, a location, the room number, and the time that it meets. We could have another course offering of the same course, the mother, but with a different room number, a different section number, a different location, different time. So you have multiple of these to one course. But that's what an attribute is. An attribute is a description of the class. So here's more detail now. The registration form is just the registration form, but we saw in the registration manager we can have processes down below, things it can do. Scheduling algorithm doesn't really. But course, we have the name of the course, the number of credits for that course are attributes, and then things we can do against it. We can open the course, or this really says how many spaces are still, or is it open or not open? That's really what that is. This is probably binary, 1 or 0. Add student is one of the operations. Student attributes are name, major, professor, name, tenure status. Tenure status is kind of interesting.
How come on registration manager, course and student info is not listed in the data element area?
Because it's over here, registration manager affects this. Okay? So the registration manager is a piece of software, probably like a module, that gives the registrar the ability to add, delete.
Yeah, but shouldn't those data objects be in between those two parallel lines there?
Oh, attributes of the registration?
Yeah, shouldn't that be in the attributes section?
So that course becomes a sub of registration manager?
Well, just so that you know what data is affecting registration.
Mm-hmm. And that could be. They talk about that in the literature. Although we're really talking about the class of being over here as course, you can show that, we're going to show it by arrows too, so let's see how that works.
Well, I guess the same thing goes with student info on the others. Apparently, if it's a parameter to a function, they don't put it in the attributes.
That's correct, because they're going to use their relationship with the class to show what they're doing. So, the relationships, and that's what we're going to get into now, providing a pathway for communication between objects. So those blocks, class blocks, were objects. We're now going to show pathways between them. So sequence or collaboration diagrams are examined to determine what links between the objects need to exist to accomplish the behavior. If two objects need to talk, there must be a link between them. 3 types of relationships are association, aggregation, and dependency. So let's talk about those. Those are going to have different symbols. Association are bidirectional connection between classes. And it's shown as a line connecting the related classes. So that registration manager in courses is going to be bidirectional, isn't it? Okay. An aggregation is a stronger form of relationship where the relationship is between a whole and its parts. An aggregation is shown as a line connecting the related classes with a diamond next to the class representing the whole. And we'll see that in a minute. So a dependency relationship is a weaker form of the relationship, showing a relationship between a client and a supplier, where the client does not have a semantic knowledge of the supplier. And that's really the algorithm that's figuring out the schedule. We'll see that in a minute. And a dependency shown as a dash line, I'm sorry, this is the one that's the algorithm. The dependency shown as a dash line pointing from the client to the supplier. So let's see how those look. So relationships are discovered by examining interaction diagrams. So taking out of the sequential view, we saw that we had a relationship between Registration Manager and Math 101, which is in courses, right? And we send a request to add student, Joe, to course. Over here, it looks like this, Registration Manager, course. There's a dependency here because it goes both ways. The course affects the Registration Manager, the Registration Manager affects the course. So we begin to look at it this way. The registration form and the Registration Manager are connected. The Registration Manager, through the add student function, goes to course, checks to see if it's open, and then adds the student. Well, see if they go through the add student to see if they can add it. Going down here, though, notice that this is the total. This is a part, and that's why the triangle is there. It's towards the total. Notice the dotted line going up the schedule algorithm. That's probably only used when the registrar is building the curriculum for next semester. They put it all in there, and then there's an algorithm that has to go out, check whether there's room availability, whether there's time availability for that room, whether they're mapping against, we've got what we call the perpetual schedule. We want to make sure that this course is offered in the evenings every semester. So that's in that algorithm. Right. The student and course offering are connected, as well as the professor for getting the roster. Does that make sense? Again, this is probably oversimplified some of the things you do, John. Just trying to get an overview of what UML does. So multiplicity and navigation. Multiplicity defines how many objects participate in relationships. It's the number of instances of one class related to one instance of the other class. So we could have a class that causes 5 things to happen in another class. And that could be like that course and course offering connection. The multiplicity there could be that although we know there's a course for Math 101, there are 10 sections. So that would be the multiplicity. So although associations aggregation is bidirectional, by default, it's often desirable to restrict navigation to one direction, and we use an arrowhead to do that. If it's, well, there it is. If it's restricted, an arrowhead is added. So, now, this looks a little bit more like what we're talking about. Registration form goes to the registration manager. You can see it's pretty much one directional. Scheduling algorithm is fed. Then we go down here to courses. From the course, we go to course offerings. But over here, we could have a student getting 3 to 10 instances from the course offerings, right? I think that's what that's saying. I think that's the multiplicity. Professor sends in one request for their schedule, for their rosters, but they could get up to 4 rosters back, meaning the professor can teach up to 4 classes.
And when there's the asterisk, it means many. It can be any asterisk.
Yeah, I'm not sure what the asterisks mean. The thing is that this form was taken off of something that probably had footnotes for the asterisks.
I would assume that the asterisk means n number of.
N
Yeah,
number.
it's
right,
one to
yeah.
unlimited.
1 to unlimited, yeah, which makes sense.
So,
Actually, I think the asterisk is generally referred to as many, 1 to many.
1 to many, yeah, that makes sense. And so up here, registration manager puts out 1 request to courses, but it could affect many.
It's unbounded.
So, inheritance, that wasn't complicated enough, is a relationship between the superclass and its subclasses. There are 2 ways to find inheritance, through generalization or specialization. So common attributes, operations, and/or relationships are shown in the highest applicable level in the hierarchy. So let's see if we can. A little more definition of that. Here, I think we're trying to show there's a registration user, which is a conglomerate of professors and students. Okay, so that's a superclass. And this comes into setting passwords and things like that. So you've got a general registration user database, which is a superclass of professors and students. And in fact, that's the only place they've got it. Okay? That makes sense? The state of an object shows the life history of a given class, the events that cause a transaction or transition from one state to another, the actions that result from a state change. State transition diagrams are created for objects with significant dynamic behavior. So if you've got an object that has a lot of behavior happening dynamically, in other words, quickly, that timing, then a state transition diagram is a good thing to have. To why it changes. So here's a state transition diagram. So from the outside, we come into an initialization where we initialize the course. If we want to cancel the course, we go down here where it's canceled, and then we're out, we're finished, right? But on the other hand, we could go over here to an add student, where the count is less than 10. We open registration for the student, we enter registration, a registered student, we exit by incrementing the count there. If our count overflows, we go down to canceling, or if the student is canceled. We cancel here, cancel the registered students, and go out. Down here, if the count equals 10, now this is going to cause the close. If the count equals 10, it's going to be a closed class. So we finalize the course and we end, or we go over and we cancel. So that's beginning to show the activity. That's what they mean by being dynamic. So that, I believe, is the end of that's the end of the slideshow. Any questions on that? Yes, ma'am.
So for the project, we need to create different diagrams. Example for that one, it looks like more like, example, when they receive the payment.
Mm-hmm.
So the system has to wait to confirmation the bank. So we need to create the diagram for that, and maybe the diagram, the flow diagram for the data lake. So we need to create different diagrams for.
Yeah, and again, it's up to you as to how, there's no like rigid, correct way to do it. What you want to do is do it in such a way that if I look at it, I can understand what your system does without knowing the programming. It's the overview. Oh, the clerk at the counter keys in this customer. It goes to the customer file and checks to see if the customer is okay for payment or something like, whatever. Or do we have on file? If it's not on file, then you go over here and you create a customer record. Does that make sense?
Yeah.
Is that in the project?
Well, in the, like for the state diagram homework assignment, this instruction was to keep it simple.
Mm-hmm.
Well, keeping it simple can be really simple.
Mm-hmm.
Is that how simple you wanted it? I mean,
Yeah.
basically,
Yeah. I just want you
it's
to,
just states.
in your case, you've done a number of them, but in anybody else's case, I want them to go through the exercise of seeing what it's like to put together a state diagram. And probably the biggest mistake is people overcomplicate them. Because you really want to make it so you saw how simple they made that thing.
I mean, it's just,
Yeah. But from that, your question about where does the billing come in got answered, didn't it? Comes from the schedule.
Yes.
Yeah. Interesting. Because that's definitely a decision. That's not a hard and fast rule. You weren't wrong. This is the way that university wanted it. So yeah, I think the simpler you make it, as long as it answers those types of questions. I think simple's better. And you know what, it's all right if you do something like a state diagram and you show it to a group and they start asking you questions about it. That's fine, because what you've done is you've opened the conversation and you're going to get data, you're going to get information from the group, because they're probably the users, that'll help you understand better what their requirements are.
is that on D2L?
Yes, it is.
PowerPoint?
If you go into, was it module 4 or whatever?
4.
Yeah, go into 4. It's at the very top, I think, under, it may be a sub under 4, first sub.
You got you got state models?
Yeah, go to state model, and then at the very top, it says UML. Over, no, let's see. Yeah, go. Unit 4.
Oh, here, right there, bottom.
Okay. That's a PDF. That's on state diagrams. It may be 5. Maybe 4 is on the right one.
UML.
Yeah.
Yeah,
Okay. Yeah, there it is at the top. UML basis.
System diagram,
Yeah.
movie doc. System diagram, system design and movie document.
The PowerPoint.
Which one is that?
Is the file UML, right there, top one?
Basic?
Yeah.
Think so?
Okay, so if you all want to spend some time on the project, that would probably be a good idea.
So you all done yet?
Sorry?
I said, are you all done yet?
Yeah, I'm done. I'm
No,
done.
Talking to the team.
Oh,
Are they done yet?